In this video, we're going to discuss the problem of nonlinear regression. And following that, we're going to see what will happen if we introduce overly complex nonlinear models and how we can avoid that. So in this example that we have, there is a set of nonlinear data that is being depicted via the blue points. We understand that the data is not linear because if we try any line, any linear line to fit our data, it's very difficult to find a line that perfectly matches our data. For this reason, we can use nonlinear functions in order to approximate those blue points. So in this example, one potential nonlinear function that can be used is a higher order polynomial. And a higher order polynomial would mean that instead of using just the raw features of the data, we go ahead and use higher order polynomials that are based on the raw features. So mathematically, this can be expressed by using a transformation function phi that takes as an input the original d-dimensional feature space and yields as an output another space of dimensions m, which is a nonlinear representation or a nonlinear combination of the input features x. An example here is that, for example, if we have a space with two features, x1 and x2, then a nonlinear function of that space could be this transformed space phi of x that contains as a first feature the feature x1, but as a second feature the square of x2, and as a third feature the cube of x1 plus the second feature x2. So now that we have this nonlinear space, we would like to fit a function, we would like to fit a regression model into that nonlinear space. And each of the dimensions, each of the features of this nonlinear space are going to be multiplied by a weight W. Now, we understand that the nonlinearity comes by the nonlinear transformation phi, while the weights W are still linear in this expression. And after having transformed our original space into this transformed space phi, when we multiplied the transformed space with our weights, we get our output label y. Now, similarly to linear regression, what we want to do is find an optimal set of weights that best approximates our data. And we can do that by calculating the RSS error between our original labels and our predicted values from the transformed nonlinear space. So instead of having a linear matrix that just contains our input features x for all our samples, like we had for the linear regression problem, now all we have is a nonlinear matrix, a nonlinear feature matrix, and each row of this nonlinear matrix corresponds to the nonlinear transformation of the original feature space. We understand that this problem has exactly the same formulation and can be solved exactly the same as the linear problem. And the reason for this is that although the feature space has been transformed in this nonlinear manner, the weight space still keeps the same linearity as it had with the linear regression. So this matrix phi is a matrix that still has some values. We still know the actual values of each of these rows of the matrix. However, what we want to find is the weights W from this RSS error. And in order to solve this equation, in order actually to find the W that results in the minimal RSS error, we have to do exactly the same computational steps that we did for the linear regression. And again, the only difference is that in the linear regression, this variable here was the data matrix X, while in this nonlinear regression, this variable here is our nonlinear data matrix phi. However, this phi is not an unknown. This phi is being computed by our training samples. Therefore, the problem with respect to the weights W remains exactly the same. Therefore, the solution again can have exactly the same form as the solution from the linear design matrix. And the same solution means that again we have this phi transpose phi. In the linear case, it used to be X transpose X, and the inverse of this multiplied by the transpose of X. In this case, it will be the transpose of I. Now, a question here arises as to how we can find our polynomial basis function phi. And this is pretty much a key in applying nonlinear regression. So many times, just having a higher order polynomial can actually work pretty well for our data. The question is though, what can be the order of this polynomial? Is the polynomial going to be a second order or 20th order? Now, for this, what we have to do is we have to do a little bit of hyperparameter tuning. And here in this example, we have our original samples, which were generated by this sinusoid function. And in these original blue samples that were generated by this green sinusoidal line, we fit 4 different polynomials of 4 different orders. So this 0th order polynomial is essentially just a constant. This first order polynomial is a line. The 3rd order polynomial is this nonlinear line, and then this ninth order polynomial is again a line that is way more nonlinear. So what we see here is that in the first 2 orders, m equals 0 and m equals 1, we can see that these 2 straight lines pretty much do not accurately represent the structure of our data. Both lines are linear, and both lines really cannot depict the complexity that arises from this sinusoidal function. However, we can see that for m equals 3, essentially when we have a 3rd order polynomial, our data can be actually pretty well fitted. And in this red line depicts this 3rd order polynomial. So we see that the error between our training samples and this red line, which corresponds to the 3rd order polynomial, is pretty good, is pretty low. Another thing that we see is that if now we have a new data sample that has been generated by this green line, which is our ground truth, then this new sample will be also very well estimated by the red line. Essentially, what we see is that the red line and the green line are pretty close to each other. And this also suggests that this red line can be very well generalized for a set of unseen test data. However, when we have a higher order polynomial, and in this case we see a 9th order polynomial, we can see that this red line that represents this 9th order polynomial doesn't represent the structure of our data at all. So we can see that this red line pretty much does not depict any of the structure that is being represented by the green line, which is the line that was used to generate our data. In this case, we also see that all the training samples have been pretty much accurately, they have 100% fit. So this red line fits our training samples, which are plotted here with the blue circles, with 0 error. However, if we had a new test sample that was generated by this green line, this new test sample would very likely have a very high error if it was estimated by this 9th order polynomial red line. And why is that? That is because this red line is really very complex for the amount of complexity in our data. And this is the core definition of overfitting. Overfitting refers to an overly complicated model that does not really fit the structure of our data. On the contrast, if we have a very simple model, like we had for m equals 0 and m equals 1, that would be referred to as underfitting. We also see that in the same example, the more we increase the order of these polynomials, the more the corresponding weight coefficients increase, the absolute value of the weight coefficients increase. And this would mean that there are specific terms in that polynomial that would really skew our model towards some direction, and that direction might not actually be a good fit for our data. So this observation that essentially when we have a very large weight values, it's also likely that we have an overfitting. This will be an observation that will be used in order to devise a strategy to avoid overfitting. And this strategy, as we will see, will be called regularization. So going back a little bit into how our error would look if we fit a polynomial model of various degrees into a set of training and a set of testing data. Let's imagine that we have the same sinusoidal example that we used before. So we can see that the more we increase the order of the polynomial, the more the error on our training data decreases. And that is why, and that is because we increase the polynomial, and the polynomial, because it is trained on our training data, it reaches pretty much a 0 error. However, when we use an unseen test set in order to test our overly complex models, we can see that we get very high errors for this unseen test set. And the reason is that the more we increase the model and the more we make the model overly complicated, then this overly complicated model would not be able to represent the inherent structure of our data. And therefore, this would lead to poor generalization. This plot is an example of how we can actually detect overfitting experimentally in our data. So we can calculate the error or calculate the performance or the accuracy of our model if we have a classification example in both a training set and a test, or better, a development set. And we can see how the performance of the model works across the test and the training set, the more we increase the model complexity. So essentially this slide says exactly the same thing. As our model becomes more complex, the performance of the training keeps improving, while on the test data, the performance will improve first, but then will deteriorate later. And based on the observation that when we have overfitting, then it is very likely that some of the parameters of our model, in this case, some of the weights of the nonlinear regression will become arbitrarily high. We are going to try to find a way to address overfitting by essentially controlling the magnitude of the parameters of our model. Another potential way to avoid overfitting would be to try to use more training data. So in this case, if instead of 10 training samples, we have 100 training samples, then even if we use a polynomial declivity that is very high, then we can still get a model like this red line here that very accurately represents the structure of our data. And the reason for this is that because we have so many training samples, these training samples can actually recover the underlying structure, and they are not really confused by the fact that we impose a high order polynomial to our model. Another solution, if we do not have enough data, is to use less features. So we can use features that we believe they are the most indicative of our outcome, or features that are not very much related to each other. Therefore, they do not provide redundant information. A more systematic way to approach overfitting is through regularization. So essentially what we want to do is that we want to penalize model parameters, in this case, weights of our regression models that are arbitrarily large, that have an arbitrarily large magnitude. However, in practice, we really do not know which parameters of the model we need to penalize. For this reason, what we are going to do is that we are going to penalize all the parameters of our model and learn our model such that it figures out by itself from the data which parameters to penalize more. Now, a systematic way to do that is basically to add to the evaluation criterion of our model. In this case, it can be the RSS error of the linear regression, another term that represents the magnitude of the model parameters. So in this case, this term, this term is the L2 norm of the weights, meaning that we add to our evaluation criterion also each weight, the L2 norm of each weight, the sum of the L2 norms of the weights. In order to control the level of regularization, we also add this lambda, which refers to how much this regularization term will be taken into account where we optimize our cost function. So what this cost function finally boils down to is that we're trying to find our weights W such that we can optimize our standard evaluation criterion that is being determined by our algorithm, for example, the RSS error in the regression. And we are also trying to keep the weights or the parameters of our model in a reasonable range. So we are trying to avoid the parameters of our model to become arbitrarily large. You must have noticed here that instead of taking the actual absolute value of our weights, in this first line, we actually took the square of the L2 norm. And the reason for that is that if we were to compute the first order derivative of this entire criterion here, it would be so much easier to compute the first order derivative using the square of the L2 norm. And this is referred to many times as L2 norm regularization. Now, another thing that we can also take into account is how many data we have. So if we have a lot of training samples, then it might not be necessary to apply such a strong regularization. For this reason, a common approach is to divide the regularization term by the number of training samples. Intuitively, if we have a large number of n, then this term here will not contribute that much to the overall loss function. And finally, we can always apply what we call L1 norm regularization, meaning instead of adding the L2 norm of the sum of the L2 norm of the weights, we can add the sum of the absolute value of the weights. However, when we apply L1 norm regularization, this will be computationally a little bit more difficult to handle when we would like to solve the optimization problem. So if we go now to the nonlinear regression problem, this would translate into essentially applying this L2 norm regularization in the residual sum of squares of our regression. And this can even be a linear regression or a nonlinear regression. The RSS error is exactly the same RSS error that we have seen from before. And to this RSS error, we also add the sum of squares of the weights. And similarly, if we have a nonlinear regression, we would have the RSS error that is being determined by the nonlinear data metrics. Now, in order to find a solution that essentially the weight W that minimizes these two costs, we can actually find the first order derivative of each of these two costs and set the first order derivative to 0. We will see as part of this handout that if we do that, we can actually find a closed form solution for both the regularized, both linear and nonlinear regression. So let's go a little bit now to prove this. In this handout, we have exactly the same problem of linear or nonlinear regression. We have our model that transforms from an input space X into an output space Y. And we have our set of training data and our set of labels. Now, the evaluation criterion for the case of regression, if we had no regularization, it would be the RSS error, which is the error that we have seen from before. And when we conduct L2 norm regularization, we add the sum of the square values of the weights into this RSS error. So here, what we do is that we go from the algebraic notation of the sum of the weights into just this L2 norm, and these two things are exactly the same. And from there, we just expand our expression in order to collect the same order of the weights into the same place. So you can see essentially that this is pretty much a very similar thing to the expression that we had when we applied linear regression and nonlinear regression without regularization. Mainly, the only thing that changes is that when we have this W transpose W, this is being multiplied by this parenthesis here. And in this parenthesis, instead of only having the data matrix, we also have these regularization terms lambda that are being multiplied with a D by D identity matrix. Now, what we want to do after that, we want to compute the first order derivative of this expression here. By computing this first order derivative, this term does not depend on W, therefore it disappears. This term only depends on W transpose, therefore the only thing that remains is this multiplier of W transpose. And this, you can think about this as if it is W raised to the power of 2, therefore the term that remains here is 2 times W times this parenthesis here. When we set this to 0, we go ahead and find this solution. So this solution is very similar to the linear regression, but again, instead of only having the data matrix in this parenthesis, we also have the data matrix which is being added to an identity matrix multiplied by the regularization term. We understand that the higher this lambda, the more the regularization will apply, And then the lower this lambda, the closer this lambda is to 0, then this solution would approximate the solution that we had in the linear or the nonlinear regression without regularization. And I'm saying here both linear or nonlinear regression, because for the nonlinear regression, the only thing that we need to do is substitute this data matrix of our original features with the nonlinear data matrix phi. So let's go back to our slides now, after we have seen that there is a closed form solution to this regularized regression problem. Another question would be, why would need regularization for linear regression? So sometimes it happens that we have a very large number of features in our linear regression models that might not all be relevant to our outcome, or they might also be very redundant with each other. So in the case that we have features that are very much associated, especially if we have collinear variables or collinear features, regularization would be a way to avoid overfitting by assigning a weight that is close to 0 to variables that have redundant information. Now here we have another small question. Assuming a set of samples that are generated from a sinusoidal function, the same sinusoidal function that we have seen, but now we are performing regularized nonlinear regression with a 9th order polynomial. So the question here is, how does the resulting model in the red line look as we increase the amount of regularization? Again, let me remind you that the more we increase the amount of regularization, the less complex our model will become. And the reason for this is that the more we increase the amount of regularization, then the more importance the cost function will have at minimizing the absolute value or the L2 norm of the parameters of the model. In this case, it would be very important for our cost function to minimize the L2 norm of these weights W0 through W9. By minimizing this L2 norm, especially if we apply a very high regularization, this would mean that the weights would become very close to 0. Therefore, this model would now become a linear line. And therefore, the correct answer here would be A, meaning that the more regularization we apply, the more the model would become a linear line, and then we would actually have overfitting, underfitting. As part of this final slide, we plot the error of our regression model against the degree of regularization for both a training set and a test set. We see that for a training set, when we start applying regularization, our model, of course, becomes less complicated. Therefore, it's less capable of accurately fitting our data at 100%. And since it is less capable, then the corresponding training error increases. Now, for our testing data, it is actually the case that if we apply regularization, the model will become slightly less complex. Therefore, it will be less likely it will be more likely to avoid overfitting, and therefore more likely to better fit our test data. So we see here this red line, and this is the point where we start applying some regularization, and we see that the testing error decreases. The testing error, in this case, it becomes flat when we apply some degree of regularization. But then, of course, if we apply an overly high degree of regularization, then our model will become too simple. And then in this case, the error on the test set will also increase. This is the end of the module that describes both the linear and the nonlinear regression. And next, we are going to see the logistic regression model.